We all encounter various forms of mushrooms in our day-to-day lives.
But did you know that when manipulated, the root-like structure of a fungus, called mycelium, may help address environmental and public health concerns? Even though some people may view fungi as gross or undesirable, certain strains of mushrooms, like reishi, have been used in Asia for their medicinal effects for more than 2,000 years. In the last decade, scientists have been experimenting with mycelium as an alternative material for infrastructure and packaging. These developments are crucial in the fight against plastic pollution. These innovations also signify potential improvement in air quality, as mycelium-based products are not dependent on petroleum-based plastic production.
Air quality is a vital concern in the 21st century. Between wildfire smoke, vehicle exhaust, and industrial emissions, it's difficult to keep poor air quality out of the home.
Ironically, the same devices designed to filter out poor indoor air quality release harmful emissions during manufacturing stage that further pollute the air and take hundreds, if not thousands of years to break down in landfills. Did you know over 100 million disposable air filters end up in landfills each year?
That's why we developed MycoAir, a 100% biodegradable air filter developed from mycelium. MycoAir strives to replace traditional air filters used in residential HVAC systems.
Since we designed our product for in-home use, our target audience includes environmentally conscious homeowners and apartment dwellers.
But how did we arrive from mycelium to air filters?
First of all, we're an interdisciplinary group of students from UC Davis.
We diligently researched the properties of mycelium and its different applications, pulling information from researchers around the world.
We read that mycelium is excellent at filtering out pollutants and chemicals from soil. We're curious if mycelium can filter out air pollution as well. We spoke to an expert on fungi, a professor at UC Davis named Dr. Rizzo. He suggested that we experiment with the strains Ganoderma and Pleurotus, also known as reishi and oyster, because of their fast growth rates. Another expert, Dr. Valeria La Saponara, gave us insights into testing the properties of mycelium.
At the onset in our project, we sought to create a biofoam that the mycelium could climb, similar to how plants climb a lattice. Our goal was to create a structurally sound, porous foam that could withstand the stress of being handled. The mycelium gradually eats the biofoam, retaining the shape of the foam.
In developing our filter, we tested many materials and methods for growing mycelium in different types of biofoam. First, we tested a soybean oil-based foam with methods adapted from researchers in Finland. This biofoam is a mixture of a surfactant, soybean oil, a blowing agent, and cellulose-dissolving pulp. However, we had difficulty initiating enough foam formation to make a large enough sample, so we explored other alternatives.
We briefly pivoted to explore a cloth-based material as a structural alternative.
We drew inspiration for this experiment from batik, an Indonesian fabric dyeing technique. In batik, artists melt wax on areas of cloth that they want to protect from the dye. After the dyeing process, the wax is ironed off of the cloth. We want to systematically block mycelium growth to allow for ample porosity.
We grew the mycelium on top of several pieces of cheesecloth laid over agar plates. The hyphae structures of the fungi linked the pieces of cloth together. To control where the mycelium grew on the cloth, we applied lines of beeswax and soy wax to the surface. We hoped these lines would restrict mycelium growth until we melted them away to open sections of the cloth that would allow airflow.
However, it was difficult to separate the wax from the cloth. When we applied heat to the cloth, the wax spread along the surface, covering all mycelium growth instead of melting off.
We're open to exploring a different textile base in the future.
Our third material study was a pulp and straw-based biofoam, adapted from researchers at the University of British Columbia. We blended a mixture of water, paper, straw, and cornmeal, and formed a foam by adding organic surfactant. We then dried this foam mixture through vacuum filtration and inoculated the solid residue with different species of fungi. After leaving it to grow for 20 days, we found it had formed a lightweight but solid material, capable of being cut into many different shapes.
This was our most successful experiment. We decided to use the straw biofoam for our final prototype. With assistance from Dr. La Sopanara, we brainstormed tests to compare traditional air filters to MycoAir. We tested the efficiency of our filter by pouring contaminated water through the center. The more we passed contaminated water through the filter, the more the water quality improved. This tells us that several layers of biofoam will likely improve the efficiency of the filter. We also looked at our filter under a microscope to visualize the porosity. Measuring air filter efficiency is an expensive and specialized process that will require more product development time. Due to budget and access constraints, we did not have the opportunity to work with the thermometers and specialized pressure chambers required for testing pollutant capture. With more time and resources, our tests will focus on porosity, water resistance, and volume of pollutant capture. We would also run a qualitative analysis to understand the thickness and shape of MycoAir in comparison to traditional filters.
But what does the total life cycle of this product look like? The first stage of the life cycle is raw material extraction. The main raw materials are paper waste, water, surfactant, and straw waste. All of our materials were locally sourced, including the surfactant. However, the use of this surfactant implies additional processing and subsequent emissions from its production. Also, if our product reaches an industrial scale, production requires a growing chamber for the mycelium, which consumes additional energy. Manufacturing of our product mainly involves blending, inoculating, and drying. Although blending the materials and inoculating the mycelium are relatively low in energy costs, the heat required will add substantial energy usage to our product. In the future, we hope to reduce drying time to lessen the energy required. In regards to distribution, most materials, like paper and straw, are common and can be sourced locally, which reduces the distance materials need to travel for the production phase.
For the usage stage, our filter is compatible with pre-existing infrastructure. It fits into an HVAC system. For the waste stage, our product is significantly more biodegradable than traditional air filters. The mycelium, straw, and waste paper in the filter can decompose in moist soil conditions. However, once the filter captures harmful pollutants, we want to break them down rather than put them in our soils. Mycoremediation is a process by which live mycelium breaks down common air pollutants. In future development, we hope to find a way of adding live mycelium to the foam to break down pollutants before final disposal. All in all, MycoAir hosts a more circular life cycle than traditional air filters. And because of our use of non-pathogenic edible species of mushroom, our product poses minimal risk to the consumer.
Our product aims to address the following Sustainable Development Goals. Goal 9, Industry, Innovation and Infrastructure. Goal 11, Sustainable Cities and Communities. Goal 12, Responsible Consumption and Production. And Goal 13, that is Climate Action.
Overall, we accomplished what we set out to explore. Sustainably sourced mycelium materials that are promising for bioremediation. Throughout our product's development, we built our ability to collaborate, communicate, and function as a team. From creating our own biofoam from scratch to navigating setbacks in our experiments, we learned so much. As for the product, we hope to continue our research in an attempt to provide an effective alternative to traditional air filters with MycoAir. That said, the initial costs of launching MycoAir are high because of the amount of time it takes for our product to grow, but the positive impacts of our product justify its initial cost. In a post-carbon future, it's crucial to explore alternatives to petroleum-based plastics. Thank you to Professor Christina Cogdell, researcher Alejandra Riz, and lab manager Andrew Yao for helping make this project possible. We would also like to give a shout out to the Canadian authors Risa, Corey, and Bilek Michael, who shared their base material NBSK all the way from Canada. Thank you for listening.